Explorer 51. Explorer 51, also called as AEC Atmospheric Explorer C, was a NASA scientific satellite belonging to series Atmosphere Explorer, being launched on 16 December 1973 at 6:18 UTC from Vandenberg boarded Delta 1900 launch vehicle. Spacecraft. The AEC spacecraft was a multi-sided polyhedron with a diameter of approximately. It weighed including of instrumentation. The initial elliptical orbit was altered many times in the first year of life by means of an onboard propulsion system employing a thruster. The purpose of these changes was to alter the perigee height. After this period, the orbit was circularized and was raised periodically to about when it would decay to altitude. During the first year, the latitude of perigee moved from about 10 degrees up to 68 degrees north and then down to about 60 degrees south. During this period, about 2 cycles through all local times were completed. The spacecraft could be operated in either of 2 modes, spinning at a nominal 4 revolutions per minute or to spun to 1 revolution per orbit. The spin axis was perpendicular to the orbit plane. Power was supplied by a solar cell array. The spacecraft used a PCM telemetry data system that operated in real time or in a tape recorder mode. The payload included instrumentation for the measurement of solar ultraviolet, the composition of positive ions and neutral particles, the density and temperature of neutral particles, positive ions and electrons, the measurement of airflow emissions, photoelectron energy spectra, and proton and electron fluxes up to 25 keV. Mission. The purpose of the Explorer 51 mission was to investigate the thermosphere, with emphasis on the energy transfer and processes that govern its state. The study of photochemical processes accompanying the absorption of solar UV radiation in the Earth's atmosphere was accomplished by making closely coordinated measurements of reacting constituents and the solar input. The data from Explorer 51 served, among other things, to obtain the angular load distribution around the satellite and compare it with the data of Explorer 32 and model the hydroxyl ion emissions in the Earth's atmosphere. Instruments. The satellite carried instruments to measure ultraviolet solar radiation, temperature, composition and density of the positive ions, of the neutral particles and the electrons, to measure atmospheric low emissions, the energy spectra of the photoelectrons and the protons and electrons flows with energies up to 25 keV. Miniature electrostatic accelerometer MACE. Miniature electrostatic accelerometer MACE. The miniature electrostatic analyzer MACE obtained data on the neutral density of the atmosphere in the altitude range from the measurements of satellite deceleration due to aerodynamic drag. The instrument consisted of 3 single-axis accelerometers, mounted mutually at right angles, 2 in the spacecraft XY plane and the other along the Z-axis. The instrument determined the applied acceleration from the electrostatic force required to recenter proof mass. The output of the device was a digital pulse rate proportional to the applied acceleration. The measurements allowed determination of the density of the neutral atmosphere, monitored the thrust of the orbit, adjust propulsion system ops, determined the satellite minimum altitude, measured spacecraft roll, and provided some attitude sensing information. Spacecraft nutations of less than 0.1 degrees were monitored. The instrument had 3 sensitivity ranges 8. -3 Earth's gravity G and Orbs monitor mode 4. -4 G between plus or minus 2% and plus or minus 10% and 2. -5 G between plus or minus 2% and plus or minus 10%. Numbers in parentheses represent errors. In addition, there may be a systematic error of up to plus or minus 5% due to drag coefficient uncertainty. The highest measurement altitude was determined assuming the instrument could sense to 0.2% of full scale. Ion mass spectrometer bins. Ion mass spectrometer bins. This experiment was flown to measure, throughout the Explorer 51 AEC orbit, the individual concentrations of all thermal ion species in the mass range of 1 to 72 atomic mass units U, and in the ambient density range from 8 eon to 5 S6 ion/cc. Any combination of the following 3 mass ranges expressed in units were selected by ground command: range A -1 to 4, range B -2 to 18, range C -8 to 72. Each range was normally scanned in 1.7 seconds approximately along orbit. Normal operation consisted in a sequence of CAC 1 to 72 units in 5.1 seconds. Laboratory and in-flight determination of spectrometer efficiency and mass discrimination permitted direct conversion of measured ion currents to ambient concentrations. The experiment's 4 primary mechanical components were guard ring and ion analyzer tube, collector and preamplifier assembly, vent, and main electronics housing. The guard ring was normally at ground potential, but it could be placed at -6 volts by command if desirable, e.g., if the spacecraft acquired a positive charge. A 3-stage bellet tube with 7 to 5 cycled drift spaces was flown and was modified to permit ion concentration measurements to be obtained at low altitudes. The frequency of the 30 volts peak-to-peak radio frequency or RF voltage varied with the mass range measured, range at -10 MHz, range B -5 MHz, and range C -2.5 MHz. Primary analog instrument output was a compressed ion current spectrum which displayed the full dynamic range of the amplifier system on a single telemetry channel. Onboard data processing provided a readout of primary experiment data in the form of 2 digital words for each peak in the ion spectrum. One 8-bit word indicated peak amplitude current and the other 8-bit word identified sweep position, i.e. species identification. Capacitance manometer. The capacitance manometer was primarily an engineering experiment to provide data on spacecraft operations. However, data from this experiment were also correlated with accelerometer and ion gauge data in evaluating satellite drag. The manometer, also referred to as pressure sensor BPSB, measured atmospheric pressure in the region below. The accuracy of the PSB gauge varied from about 10% to about 40%. The PSB consisted of 2 circle, thermally controlled chambers, separated by a thin membrane stretched flat and under radial tension. Any deflection of the diaphragm caused by a pressure differential between the 2 sides caused a change in capacitance between the diaphragm and an adjacent electrode, which was measured by an alternating current AC bridge circuit. Air was permitted into one of the chambers through 2 ports 180 degrees apart and perpendicular to the spacecraft's spin axis. Thus, the wave ram pressure differential was sampled twice each spacecraft revolution. Closed source neutral mass spectrometer. This experiment measured in situ the spatial distribution and temporal changes of the concentrations of the neutral atmospheric species. In addition, new insight into in-situ measurement techniques was obtained from comparisons of these measurements with those obtained from other onboard experiments, namely, Open Source Spectrometer 1973-101-7, Solar Extreme Ultraviolet UV Spectrophotometer 1973-101-6, and Density Accelerometer 1973-101-2. The mass spectrometer sensor had a gold-plated stainless steel thermalizing chamber, an ion source, a hyperbolic Roth quadrupole analyzer, and an off-axis electron multiplier. 5 different sequences of mass selections were available and, expressed in atomic mass units U, were I geophysical -1, 2, 4, total 16, 28, 32, selected 40. B analytical -12, 14, 18, 20, 22, 30, 44, calibrated 0. C individual selected, any mass 1 to 44. D sweep digital -1, 2, 3, 4, 5, 45 and 3/16 unit steps. E sweep analog -2, 3, 4, 5, 45 continuous. 5 operational formats were available and selected by ground command, and each one contained a different combination of the 5 mass selection sequences listed above. When operating in the normal format, the analyzer measured all masses in the range 1 to 44 with emphasis on hydrogen, helium, oxygen, nitrogen and argon. Another format was optimized for minor constituent studies of any individual gas species in the measured range. Spatial resolution was determined primarily by the mode of spacecraft operation. In orbit, the pursuit spectrometer was opened, and the atmospheric constituents passed through a knife-edged orifice into the thermalization chamber and ion source. Selected ions left the quadrupole analyzer through a weak focusing lens and were accelerated into a 14-stage electron multiplier, where they would turn 90 degrees to strike the first dynode. For each impacting ion, the multiplier output was a pulse of 2 S6 electrons. These output pulses constituted the measurement, and the current rate was proportional to the chamber density of the selected species. These density values were then converted to ambient concentrations. The analyzer normally operated at a resolution of 1 unit U over the mass range. Pulses occurring during 0.15 second integration intervals were accumulated in a 16-bit counter. Multiple integration periods up to 16 were assigned to each measurement for less dense atmospheric species. Automatically selected ranges of ionizing electron currents were used. The overall dynamic range of the measurements was greater than 1 SFN. Cold cathode ion gauge. The cold cathode ion gauge flown on Explorer 51 AEC was primarily an engineering experiment to provide data on spacecraft operation. However, data from this experiment was correlated with accelerometer and capacitance manometer data to evaluate satellite drive performance. The ion gauge, also referred to as pressure sensor PSA, measured atmospheric pressure in the region between and above the Earth's surface for values of atmospheric pressure between 1.3 mNs3 to 1.3 mNs7 MB. The estimated accuracy of the PSA was plus or minus 20%. The cylindrically shaped sensor package consisted of a wedge-shaped orifice, a cathode near ground potential, an anode operating at about 1300 VDC, and a permanent magnetic field of about 1600 Gauss. The gauge contained no primary source of ionizing electrons. The discharge was initiated by field emission and was self-sustaining at a pressure above 1.3 mNs7 MB. The ion current was collected at the cathode. The sensor was mounted on the spacecraft, with the orifice perpendicular to the spacecraft's spin axis, which was normal to the orbital plane. The instrument could be operated in 2 modes, spinning or to spun. When the spacecraft was in a spinning mode, the PSA alternately sampled the ram and wake pressure. When the spacecraft was in the spun mode, the PSA faced 30 degrees from the direction of motion. Data from this experiment were not tape-recorded, but was observed in real time. Cylindrical electrostatic probe CEP. Cylindrical electrostatic probe CEP. The CEP consisted of two identical instruments designed to measure electron temperatures, electron and ion concentrations, ion mass, and spacecraft potential. One probe was oriented along the spin axis of the spacecraft, normally perpendicular to the orbit plane, and the other radially so that it could observe in the direction of the velocity vector once each 15-second spin period. Each instrument was a retarding potential angular probe device that produced a current voltage IV curve for a known voltage pattern placed on the collector. Electrometers were used to measure the current. There were two systems of operation, one with 2 modes and another with 3 modes, using collector voltage patterns between plus and minus 5 volts. Most modes involved an automatic or fixed adjustment of collector voltage limits and /were electrometer output such that the region of interest in the IV profile provided higher resolution. Each system was designed for use with only one of the probes, but they could be interswitched to provide backup redundancy. The best measurements in the most favorable mode provided 1 second time resolution, electron temperature between 300 degrees K and 1.0 F for degrees K, 10% accuracy, ion density between 1.0 F and 1.0 S of an ion/cc terminus, 20% accuracy, electron density between 50 and 1.0 S electron/cc, and ion mass at ion densities above 1.0 F ion/cc. Each probe had a collector electrode extending from the central axis of a cylindrical guard ring. The long guard ring was at the end of a boom, and the collector extended another beyond the guard ring. The boom, guard, and collector were in diameter. Extreme Solar Ultraviolet Monitor SM. Extreme Solar Ultraviolet Monitor SM. The Extreme Solar Ultraviolet Monitor SMA absolute broadband spectral radiometric measurements of the solar EUV flux from 200 angstrom to Lamin alpha tau 16 and made precise measurements of the temporal variability approximately 1% per solar rotation. The instrument consisted of two identical windowless EUV photodiodes with aluminum oxide cathodes and a filter wheel containing two sets of unbat metallic filters, aluminum, tin, indium, in an open position. A visible light diode measured the pinhole transmittance of the filters to determine the white light background. The tilt angle of the instrument relative to the +D spacecraft axis was optimized for the maximum viewing time of the Sun in both spinning and spun spacecraft modes. The instrument field of view was 60 degrees. The nominal bandwidths for 50% of signal were 270 to 550, 570 to 584, 800 to 935, and 1216. Low energy electrons LE. Low energy electrons LE. This experiment provided direct measurements of the energy input into the upper atmosphere due to electrons and protons in the energy range of 0.2 to 25 keV. The experiment acquired differential measurements of the energy influx and angular distribution. There were two detectors measuring electrons and protons from 0.2 to 25 keV in 16 logarithmically spaced steps, and one detector measuring 5 keV electrons continuously. Each detector consisted of a cylindrical electrostatic analyzer for species and energy selection, and a spiral-tron electron multiplier for particle detection. Energy distributions were obtained by applying different fixed or step voltages to the diffraction plates. Distributions and angle were measured using the spacecraft spin and the analyzer's positions on the spacecraft. In the spun modes, measurements were obtained at 45 to the spacecraft equator and radially away from the Earth. Detector look angles were chosen to give optimum magnetic pitch angle coverage when the spacecraft was moving either poleward or equatorward. All detectors were identical in construction and used 1x6 mm entrance apertures. Counts were accumulated over 55.7 ms and readout each main telemetry frame 62.5 ms. The two-step detectors moved one energy step once each main frame with the same accumulation time, requiring about 1 second for a complete cycle of steps. Magnetic ion mass spectrometer MIMS. Magnetic ion mass spectrometer MIMS. A magnetic ion mass spectrometer was flown to measure in situ the concentrations of the ambient ion species in the mass range from 1 to 90 atomic mass units U. It was mounted on the satellite equator normal to the spin axis, and the entrance aperture faced forward when the spacecraft was in a spun mode. The electric and magnetic fields were arranged to produce a mass spectrum along the focal plane following the magnetic analyzer. 3 slits were placed along the focal plane in appropriate places to simultaneously collect ions in the mass ratios 1 to 4 to 16. Ionospheric ions were accelerated into the analyzer system by a negative voltage that varied from -1060 to -225 volts. The 3 mass ranges measured simultaneously were 1 to 4, 4 to 16, and 16 to 90 units. Following each slit was an electron multiplier and a logarithmic electrometer amplifier detector. The detector output could be measured directly for an analog output, or it could be fed to a peak circuit that determined the amplitude of each peak in the spectrum. Only the amplitude of each peak was telemetered in the primary peaks mode, and in this mode the time required to simultaneously sweep all three mass ranges was 1 second. Other modes of operation were possible. In the analog short mode, the three mass ranges were swept in 4 seconds, alternating with 1 second peaks mode scans. An 8-second sweep was required in the analog long mode, again alternating with 1 second peaks mode scan. An option existed in the LOT mode to continuously measure any set of mass numbers in the ratio 1:4:16 to give high spatial resolution. Neutral atmosphere temperature NATE. Neutral atmosphere temperature NATE. This experiment measured the kinetic temperature of the neutral atmosphere by determining the instantaneous density of molecular nitrogen in a spherical chamber coupled to the atmosphere through a knife-edged orifice. Analysis of the measured molecular nitrogen density variation over a spin cycle with the knowledge of the satellite's motion and orientation led to a determination of the ambient temperature, independent of scale height. A measurement of the ambient nitrogen density was also obtained. An alternate measurement of neutral temperature was also undertaken, using a baffle inserted in front of the orifice to intercept a portion of the gas particle stream entering the chamber. When the satellite was in the D1 mode, the baffle was made to oscillate in the stepwise fashion to interrupt the particle stream seen by the orifice chamber. These chamber density variations were interpreted to yield the neutral gas kinetic temperature. A dual-filament ion source sampled the thermalized molecular nitrogen in the chamber and produced an ion beam density proportional to the nitrogen chamber density. From the source, this ionized nitrogen beam was directed from a quadrupole analyzer tuned to pass those particles whose mass-to-charge ratio n/q was 28 onto an electron multiplier. The output pulses were amplified and counted in a 16-bit accumulator. The experiment also provided measurements of neutral atmospheric composition when commanded into the appropriate mode and for the first time measured the local wind vertical motions. The wind values were determined by measurement of the stream position relative to the satellite velocity. When the spacecraft was in the D1 mode, the nitrogen density was measured except when a particle stream was interrupted by the baffle. The sensor was vacuum sealed prior to launch and opened to the atmosphere after the spacecraft was in orbit. Open source neutral mass spectrometer. The objective of this experiment was to contribute to a study of the chemical, dynamic, and energetic processes that control the structure of the thermosphere by providing direct, in situ measurements of both major and minor neutral atmospheric constituents having masses in the range from 1 to 48 atomic mass units (U). A double focusing method shows a magnetic deflection mass spectrometer with an impact ion source was flown. 2 ion collectors were included to measure ions differing in mass by a factor of 8, that is, the two mass ranges covered were 1 to 6 units and 6 to 48 units. In the ion source, the neutral species were ionized by means of electron impact. At altitudes greater than, ion currents were measured with an electron multiplier counting individual ions. Ions were accumulated for 1/20 seconds before automatically switching to a different mass number. While complete mass spectra could be swept, in the common mode of operation peak stepping was employed, with readings on the principal peaks in the mass spectrum being repeated approximately every 0.5 seconds and on other species less frequently. Data below were measured using an electrometer. In addition to the peak stepping mode, there were several other operating modes which were selected by ground command. In the fly-through mode, the ion source voltages were adjusted so that there was no electric field to draw ions out of the electron beam when they were formed. Ambient particles striking the ion source retained energies less than 0.1 eV, which was not high enough to overcome the negative space-charged potential holding the ions in the beam. Those ambient particles that did not strike the ion source retained their incoming energy of several eV after ionization and escaped into the accelerating region of the analyzer. The electron accelerating potential was 75 eV in normal mode operation and was 25 eV in the fly-through mode. In another operating mode, the instrument switched automatically to a sequence of masses of particular interest such as, e.g., between masses 16 and 32 or between masses 28 and 32. Photoelectron spectrometer (PES). Photoelectron spectrometer (PES). This experiment was designed to provide information on the intensity, angular distribution, energy spectrum, and net flow along field lines of electrons in a thermosphere with energies between 1 and 500 eV. The instrument consisted of 2 identical oppositely directed hemispherical electrostatic analyzers and 30 operating modes. Each spectrometer had a relative energy resolution of plus or minus 2.5% and a geometric factor on the order of 0.1 cm2 SR, independent of electron energy. 3 separate energy ranges could be sensed, 0 to 25, 0 to 100, or 0 to 500 eV. Measurements from these intervals could be sequenced in 5 different ways. Data could be taken from either sensor separately or alternately with time resolution varying from 0.25 to 8 seconds. There were 2 deflection voltage scan rates determined by a spacecraft clock. This voltage was changed in 64 steps and was done at 4 or 16 steps per telemetry frame. With 16 frames/s, this allowed a choice of either one 64-point spectrum or 4 16-point spectra in 1 second. The longest 8-second cycle of data involved observations using increasing voltage steps for the lowest, middle, lowest, and highest energy ranges in that order for 1 second each. A repeat for decreasing voltage step completed the cycle. Retarding potential analysis/drift meter or PA. Retarding potential analysis/drift meter or PA. This experiment was designed to determine vector ion drift velocities, ion concentration and temperature, and spacecraft potential. An ionospheric irregularity index was also obtained from the ion concentration sensor. The experiment consisted of a retarding potential analyzer with 4 planar sensor heads. The sensor head used for ion drift measurements was co-located with another head, and all were spaced nearly equally, looking outward from the satellite equator. Since the satellite's spin axis was perpendicular to the orbit plane, these heads could observe along the spacecraft velocity vector in either the spin or spun mode of the spacecraft. The primary objective of this experiment was to provide accurate ion temperatures, with other measurements being of secondary importance. 3 of the sensor heads were similar. They had 2 grounded entrance grids, 2 retarding grids, a suppressor grid, a shield grid, and a collector. A linear sweep voltage 32 or 22 to 0 volts, up or down, was normally applied to the retarding grids, and 0.75 second. Interpretation of the resulting current voltage profiles provided the ion temperature, the ion and electron concentration, some ion composition information, vehicle potential, and plasma drift velocity parallel to the velocity vector. 2 of the 3 similar sensors had an additional grid between the entrance and retarding grids in order to protect inner grids from ion bombardment during electron measurements. The other significant feature of these 2 sensors was that a small positive collector bias could be applied to assure adequate access of thermal electrons to the collector. With a retarding grid at constant 0 volts, current changes could be observed for 3 seconds periods to obtain gradients of ion concentration. Electron parameters were measured in a manner similar to ions. Ions in mass ranges 1 to 4, 14 to 16, 24 to 32, and greater than 40 atomic mass units could be identified. The 4th sensor head was for the ion drift velocity measurements, and consisted of 4 grounded grids, a negatively biased suppressor grid, and a 4-segment collector. Differences in various collector segment currents provided ion drift directional component information. Solar EUV spectrophotometer use. Solar EUV spectrophotometer use. The extreme ultraviolet spectrometer was used to observe the variations in the solar EUV flux in a wavelength range from 140 to 1850 and the atmospheric attenuation of various fixed wavelengths. This provided quantitative atmospheric structure and composition data. The instrument consisted of 24 grazing incidence grating monochromators, using parallel slit systems for entrance collimation and photoelectric detectors at the exit slits. 12 of these monochromators had wavelength scan capability, each with 128 selectable wavelength positions, which could also automatically step scan to these positions. The other 12 monochromators operated at fixed wavelengths with fields of view smaller than the full solar disk to aid in the atmospheric absorption analysis. The spectral resolution varied from 2 to 54 depending upon the particular instrument. The field of view varied from 60 x 60 arc minutes down to 3 x 6 arc minutes. All 24 monochromator entrance axes were co-aligned parallel. A solar pointing system could point to 256 different positions, execute a 16-step one-dimensional scan or a full 256-step raster. The time resolution varied from 0.5 second for observing 12 fixed wavelengths up to 256 seconds for programming the use through all possible modes. Temperature alarm. This engineering experiment measured the impact temperature during low period. Ultraviolet nitric oxide of no. Ultraviolet nitric oxide of no. This ultraviolet nitric oxide experiment of no consisted of a 2-channel fixed grating epiphaste spectrometer which measured the EVLO in a 1.0 gamma band and a 15 a region centered at 2149 at. The observed intensity was produced by resonance fluorescence of sunlight by the nitric oxide molecules in the instrument's field of view. The intensity profiles obtained yielded altitude profiles of nitric oxide density as a function of time and location. Profiles were measured along the track of the satellite at times when it was on the sunlit side of the Earth. The remote sensing character of the OVNO experiment permitted measurements of nitric oxide to be made at altitudes both above and below satellite perigee. As the spacecraft spun, the spectrometer, which looked outward through the rim of the satellite, repeatedly at its field of view carried down through the atmosphere onto the Earth's limb, and altitude profiles of the emitted air glow intensity were obtained. Below some altitude, the measured signal at 2149 was contaminated by Rayleigh scattered sunlight. To correct for this contamination, a second channel measured only scattered light intensity in a 12 region centered at 2190. The 2 channels were optically and electrically independent. Nitric oxide airglow intensity was determined by taking the difference between these 2 measurements. The sensor's spherical fused quartz telescope mirror had a 125 mm focal length and focused incident light on the entrance slit of the spectrometer. From this slit, the light struck one half of the EBIT mirror and was collimated onto the grating. The 3000 600 lines per mm grating returned if collimated to the other half of the mirror, and the light was focused on 2 exit slits. The spectrometer field of view was 4 degrees x 1/4 degrees, with the long axis parallel to the spacecraft spin axis, and therefore parallel to the viewed limb. In normal operation, each channel was integrated for 20.8 ms and was read out alternately at 10.4 ms intervals. The instrument was protected against contamination from internal scattering of off-axis and dispersed light. Visible airglow photometer VAE. Visible airglow photometer VAE. This experiment contained a filter photometer designed to measure various airglow and auroral features in the spectral range between 3000 and 7500. The primary information obtained from this experiment was the rates of excitation of the atomic and molecular constituents of the thermosphere. For the Explorer 51 AEC mission, the following 6 specific lines and bands were chosen for study since they play an important role in the photochemical energy balance of the atmosphere expressed in angstroms: 3,371, 4,278, 5,200, 5,577, 6,300, and 7,319. The emissions were measured in pairs: 5,577 and 6,300, 7,319, and calibration: 3,371 and 5,577, 5,200 and 7,319, 4,278 and 3,371, calibration, and 5,200 and 6,300 and 4,278. 2 optical systems viewed at right angles to each other. Each one employed a combination of a simple objective lens and field stock to define the field of view, and each contained a multi-stage light baffle. The wide-angle high-sensitivity system designated Channel 2 had a field of view of 3 degrees half angle, and was used to measure the night glow, day glow of the satellite, and other weak emission features. The less sensitive system designated Channel 1 had a field of view of approximately 0.75 degrees half angle, and it was used for day glow and night glow horizon measurements, as well as discrete auroral features which showed strong spatial gradients. Both optical channels had a diameter of. They shared a filter wheel that contained 6 interference filters at the wavelengths identified above, and 2 other positions. One was a dark position for noise measurements, and the other was a calibrate position. The dynamic range of the instrument was 1. I 16 photons per SM21 S6 Rayleigh, in order that the sensors would respond in a fraction of a second to large changes in surface brightness without any noticeable enhancement in the background current rate. Each one contained a 1/100 attenuator and an electronic circuit to back bias the cathode. With these protective features, it was possible to measure a dark feature with no apparent enhancement in background within 120 ms after a direct view of the sun. Photons reaching the cathode were recorded using a pulse counting system.